Hello everybody, in this video we are going to talk about another combinational circuit design which is nothing but a 4-bit gray code to binary code converter. Now let's go through the problem. This is problem number 4.7 from Digital Design by Moris Mano's 5th edition. And it is asked to design, and we are asked to design a combinational circuit that converts a 4-bit gray code which is given in table 1.6 to a bit 4 binary number. Implement the circuit with exclusive OR gates. Okay, so we are going to do only this A part. Let's get started. So this is table 1.6 in which the gray code is given for the decimal equivalent. So for this decimal equivalent 0, the gray code is 0000. Okay, for 1 it is 0001, and for 2 it is 0011, and for 3 it is 0010. So what is the speciality of this gray code? So when you go from one value of this gray code to another value, you will be getting only one bit change. Okay, so that plays major role in very important applications. Okay, so here you see it, when you go from 0 to 1, you have one bit change. When you go from this 1 to 2 value, again you have only one bit change. So what's the meaning of that one bit change? Here you have the initial value as 000 for this gray code for decimal equivalent of 0. Then for 1 you have the value of 0001. So here you have this one bit change at this LSB alone. Okay. Now when you go from this first value number, decimal value number 1 to 2, it is 0011. So if you look at this, only this bit alone now changed, isn't it? So from 1 to 2, when you move from 1 to 2, this LSB bits are the same, but this bit value alone is changed. This is the changing bit. Okay, one bit value change. Then when you move on to this value 3, then it would be 0010 alone. Okay, so which one changed now? If you see, this one alone is changed from the previous value, isn't it? So these two values are the same, these two values are the same, these two values are the same, but this LSB bit alone changes its value. Okay, so this is how we have one bit change in the gray code. So similarly here you see, for 4, value 4, we have this 0110. So now you refer this previous value, it is 1010. These are all the same values, but which one changed here? The 0 to 1 alone changed. Okay, then similarly when you look at this 4th value and the 5th value, these two, if you refer, these 011 are the same. Which one has the one bit change? This 01. Okay, LSB bit alone change. This is how all the values will be having one bit change from its previous value as well as the next value. Okay. Okay. So based on this table 1.6, we have placed the gray code value. Since it is a 4-bit value, we have named it as G3, G2, G1, G0. Similarly, binary, we named it as B3, B2, B1, B3, B2, B1 and B0. Okay. So without going for any mathematical calculation and all, we have placed this gray value as such from this table. Okay. So it is 00001. Like that we have placed all the values. And the binary equivalent we know very well, isn't it? 0 is equivalent to 0000. One value is 0001, 0010, then 3 values 0011. Like that we have placed all this value. You know very well If you don't know, you can refer my previous videos how to write the binary equivalent of the decimal. Okay, you can do it by three methods I have told. In three ways you can convert this decimal value into binary. The first one is you can do it by repeated division. Second way you can go by 8421 code method, weighted sum. Okay, and the third one I used to tell you a very shortcut method. So in the repeated division, if you want to write the value 7, okay, so you have to divide it. So if you want to know the value of 7, then you have to go for repeated division. So divide it by 2 means this is 3 2s or 6, remaining 1. Again you can go for division because this 3 is greater than 2. So it is one time you can divide remaining 1. Okay. And this 1 is less than 2, so we cannot go for further division. So then now you can write the answer starting from here. So it is 111. Okay. Since it is a 4-bit value, you can add a 0 at the front. So this is the binary equivalent of the decimal value. Okay. 7. This is how we do using this first method. What is second method? 8421 code. So 8421 code, in this if you want to convert this 7 decimal into binary, so here you can look for this. This 4 plus 2 plus 1 gives you 7. So in this you can put a 1. So in this you can put a 0 for 8. For the remaining you can put 1. Okay, so suppose if you want to convert 15 into binary equivalent, then here you can put this as 8 plus 4. We know this 8 plus 4 plus 2 plus 1 gives you 15, isn't it? So you have to place ones for all this 8421 code. Similarly, if you want to convert this 10 into this 8421 code, so 8 plus 2 will give you 10, isn't it? So place ones here. The remaining you can put zeros. So this is how we can do conversion. This is the second method. The shortcut method, or the third one, is we have this B3, B2, B1 and B0 values. I have told you for this, how many, the combination is, we have 4 bits, isn't it? So it is 2 power 4, that means you have 16 combinations. 16 input combinations will be available. So you can place it like 0, 1, 0, 1, 0, 1, 0, 1 for LSB. Like that you have to put 16 combinations here, 0 1 0 1, like that it goes on toggling for 16 times. And then for this B1 it is 0 0, then 1 1, 0 0, 1 1, like that it goes on till 16 values. Okay, then for this B2 it is 4 zeros followed by 4 ones, like that you can write. Again 4 zeros followed by 4 ones, like that you can do it. Okay, for B3 it is the last, the MSB bit, isn't it? Most significant bit. The LSB is least significant bit. Okay, for MSB, so you have to place 8 zeros here, then it is followed by 8 ones. In that way you can write all the values. So this is the easiest way, or the shortcut method. Okay, now we'll proceed. So in that way we have placed all these binary values corresponding to this gray code. So gray code value is written from this table and the binary value is written using shortcut method. So we have completed this. So in this you should know that this gray code is your input value and this binary represents your outputs. So how many outputs you have? 4 outputs we have. Okay, so you will get 4 different Boolean expressions. In this, we are not going to write the Boolean expression directly for this B3, B2, B1 and B0. Instead, we are going to have it from the K-map only. Because if you see here, we have 8 number of ones, isn't it, for this. So for each and everything, if you write the Boolean expression, it would be a tedious process. So what do we do is, instead of having the Boolean expression first and then placing it in the K-map, we are directly moving on to the K-map. By looking at this values from the table, we can place the ones. See here, it is 1 here. So that one corresponds to the input combination, this 1100. So you have to look here as 11, this 00 here. This 1 1 and then 0 0, so that corresponds to this 12th cell. Okay, then look at this one that corresponds to 1101. So where is 1101? This 1 1 and then 0 1 here, so it is 13. For 13 you have to place a 1. Okay, like that you have to place the ones for this. Then the next value is here, this one, isn't it? That corresponds to 1111. So it is 15, isn't it? 111. So we place a 1 here. Then for this one, sorry, this one, it is 1110. 1110. So look at here, 1 1. Then here you have this 10. 1110 is available here. So for this 14, you place a 1. So we have placed 4 ones now so far. Now we are going for this one. This one at B3, that corresponds to 1010, isn't it? So 1010, you come over here, it is 10, then this 10. So here we are placing a 1. Then you go for the next one. So here this one, isn't it? So for this one, it is 1011. So 1011 means here 10. So 11, then it is 11 here. For this 11, we place a 1. Then the next one combination is, for this one, it is 1001. 1. So we know it is 9, isn't it? 1001 means 9. So place a 1 here. Then the last one, this corresponds to 8. 1000. So it is 8 value. 1000, that means 8. So you place a 1. So we have 8 number of ones which are adjacent to each other. So we can form a loop for this, that is an octet. So we form an octet. Octet means consists of 8 number of ones, isn't it? So after grouping them, how to write this expression? Here on the side, if you look at here, you have 1 1 1 0. So the 1 and 0, they are changing, so they can be cancelled. Here you have only 1. So that corresponds to this G3. But column wise, if you see all the 4 columns are covered, that means this is 1. So finally we have G3 dot 1, that means G3 alone. So that G3 is the literal for this B3. Okay, or the expression for this B3. So that corresponds to this. We are going to write the expression for this B2 by directly applying the values into the K-map. Okay. So we look at this B2. Here you have a 1. That 1 corresponds to 0, 1, 1, 0. So whereas 0, 1 and 1, 0 means this. So that corresponds to the 6th value. And then the next one, this one, that corresponds to the 0, 1, 1, 1. So it is 0, 1, 1, 1 here. Okay. So it is 7th cell where we place a 1 here. Then for this third one, that corresponds to 0, 1, 0, 1. So you have this as 0, 1, then 0, 1. So that corresponds to 5th cell. Okay. Then we have this one that corresponds to 0100. So 0100 means it is for 4. A common mistake will be made by us if you take this as 0 value, 1 value, 2 value, 3, 4 like that if you write, and if you try to make it into this case K map, then it will end up with wrong answer. Okay, so don't compare this with the decimal equivalent for the gray code. If you write the 0, 1, 2, 3, 4 means that is the decimal equivalent for binary, not for the gray code. So if you want to find out the input combination of this gray code for the outputs, then directly refer this table. Okay, don't go for this binary equivalent and all. It is different, right? So now we have written these four values. Next, here you have zeros, then you have these four values as ones. So for this one, what is the input combination? It is 1010. So here it is 10, then here it is 10, that corresponds to here 10. So place a 1 here. Then this one that corresponds to 1011. So it is 10 here, 11 here, so place a 1 here. Okay, that is 11. Then for this one, it is 1001, 1001. So that corresponds to this 9. And finally, for this one, it is 1000. That means 8, isn't it? 1000. So we have this as 8. So we are placing ones here. Now, these four ones can be combined and these four ones can be combined, but we cannot combine them as octet, isn't it? They are not adjacent. So here we can form a squad. We can form a quad here. Similarly, here also you can form another quad. So this is loop 1, this is loop 2, and this value is here. If you refer this side, that is G3 bar. The 0 represents bar. Okay, so G3 bar, this represents G2, and this column wise everything is covered, so it is equal to 1. So G3 bar dot G2 is the expression for loop 1. So when you consider this loop 2, here we have combined this, isn't it? So that corresponds to this 1010 represents G3 G2 bar, and column wise no literal is available. So the answer for loop 2 is G3 G2 bar. Now we have to combine, isn't it, to get this B2 expression. So it is G3 bar G2 plus G3 G2 bar. So that is nothing but our exclusive OR function. That is G3 exclusive OR with G2. So we got the expression for B2. Now we move on to this B1. So if you see this B1, so for this B1 we have the values as 1 1 for these two corresponding to this. As I have already told you, this corresponds to only this binary equivalent. So don't go for this. So for this one, we have the 0011, isn't it? Okay. So it is 0011. So place a 1 into this 3. Then here a 1 that represents 0010 input combination corresponding to this one. Okay. So that is nothing but 2. So place a 1 here. 00, then 1010. So it is 2. Okay. Then here we have a 1. So that corresponds to 0101. So it is 01, then 01. So place a 1 here. Similarly for this it is 0100. So it is 0100 means 4 values. So place a 1 here. Then we go for this. This corresponds to 1111. 1111 corresponds to 15, isn't it? 1111 corresponds to 15. Place a 1 here. Then this one that corresponds to 1110. So 1110 corresponding to this one, right? 14. Then we have a 1 here that corresponds to 1001. That means it is 9, isn't it? 1001 means 9 here. Then the last one is 1000. That means 8. So for 8 we place a 1 here. Then we try to combine them. Here we can combine them as pair. Okay, no octet, no quad. Only pair is here available. So we have 4 pairs and we can write the expression for this. For this it is here on this side it is G3 dash G2 dash, and on this side this G1 alone is available, G not get cancelled because this 1 and 0 value. So it is G3 bar, G2 bar and then G1. Then for this particular loop it is here 0 1 that corresponds to G3 bar G2. On this side it is G1 bar, G naught is cancelled. Okay, so we have this G3 bar G2 G1 bar. Then for this particular loop it is here on the side G3 G2, but here this G3 exists, G naught get cancelled. Okay, so G3 G2 G1. And for the last loop it is 1 0 here on this side, the 0 0 0 1. That means the 0 only exists, the 0 and 1 it changes its value. That G naught changes its value, it won't be available. So here it is, this 1 0 represents G3 G2 bar, and here it is G1 bar, isn't it? So the answer for B1 is, we have to combine all these 4 terms, isn't it? G3 bar, G2 bar, G1 plus G3 bar, G2, G1 bar plus G3, G2, G1 plus G3, G2 bar, G1. Okay. So now if you look at this, here for these two terms, this G3 bar is common, so we take it outside. Remaining here we have this G2 bar, G1, and here we have this G2, G1 bar. Okay. So plus here this G3 is common in the third and the fourth term, so you take it outside. Inside this we have this is G2 G1 plus G2 bar G1 bar. So here it is G3. In the next step we can write this. So we can write this G3 bar here. But what about this? It is G2 bar G1 plus G2 G1 bar. That means it is exclusive OR function, isn't it? So we can write it as G2 exclusive OR with G1 plus this plus. Okay, then this G3 comes here. What about this G2 G1 plus G2 bar G1 bar? That represents exclusive NOR function. So we write it as G2 exclusive NOR with G1. Like that we can write. Then here you can write again. We can go for the next step. In this we write this as G3 bar ANDed with G2 XORed with the G1 plus this G3 into, here you see it is NOR, XNOR gate, isn't it? It is XNOR function, isn't it? That can be written as XORed with the bar, isn't it? So G2 XORed with the G1, the whole bar. So here if you see it is G3 bar into G2 exclusive OR with the G1 plus G3 into G2 plus, that is exclusive OR G1, the whole bar. Okay, so if you take this as A bar, this is B, A bar B, this is again plus A B bar, like that we got. That means the answer is exclusive OR function, isn't it? So here it is G3 exclusive OR with G2 and G1. Now we move on to the last one, B naught. So to get the output expression for B naught, and how to place these ones for B naught. So into the K map, here if you see 1 for this 0001 is 1. So 0001 place a 1 here. For this one it is 0010. So 0010 is 2, place a 1 here. Then for this it is 0111, that means 7. So place a 1 here. Then for this it is 0 1 0 0, that means 4, so place a 1 here. Then for this it is 1 1 0 1, 1 1 0 1 is 13, so place a 1 here. Then this one is 1 1 1 0, that means 8 plus 4 plus 2, isn't it? 12 plus 2 14, so for 14 you place a 1 here. Here it is 4, you place a 1. Then for this is 15, you place a 1. Then it is 14, place a 1. Then here it is 13, this one for this 14. Then this one for this 1011, that is 11. So place a 1 here. One for this 1000, that means 8, place a 1. So okay. So for all this we have placed ones, and they cannot be combined, so we have to write the message. Okay, so this scheme up is not needed. You can directly write the expression also. If you want, you can also draw the scheme up. It is again another process, another time consuming process. Okay, here I have looked into this. That means for this one, it is 0001, isn't it? So it is G3 bar, G2 bar, then G1 bar, G dot, like that I have written. Then for this 2, it is 0010, right? So G3 bar, G2 bar, G1, G naught, that is written here. G1, G naught bar. Then if you look at this here, that corresponds to this one, corresponds to this G3 bar, G2 into this G1 bar, G naught bar. So here it is G3, G3 bar, G2, then here it is G1 bar, G naught bar. Okay, plus this one for the 7th, right? This one corresponds to this 01 means G3 bar. Here we have written G3 bar, then G2, and column wise it is G1, G0. That's what written here. Then for this one, it is 1 means G3, G2. Where is it? Just delete it. G3. So for this 13, it is G3, G2. Here it is. Okay. Then G1 bar, G0. So that is written here. Then plus for this one, it is 1 means G3, G2. Here again 10. This represents G1, G0 bar. So it is written here. Then this one, it corresponds to 8. Okay, so it is 10 means G3, G2 bar. Here it is G1 bar, G0 bar. Like that you will have to write. Plus this one corresponds to what? 10 and 11, right? So it is 10 is G3, G2 bar. Here it is G1, G0. Like that we have written. So either by writing this from the K-map, or you can directly refer this and you can write it. Okay. So anyhow, it is a somewhat tedious process, time consuming process. That's it. So now you got it. Now we can combine with the similar terms. So look at here. In these two terms, we have G3 bar, G2 bar common. Okay, so we take it outside. Then you get this as G1 bar, G0 within bracket plus this G1, G0 bar. So you know that this is very well exclusive OR function, isn't it? Okay, so that would be brought over here. See here the first term G3 bar, G2 bar, and then this one is written as G1 exclusive OR with G0. Similarly, you consider these two terms, second, third and fourth. In this G3 bar, G2 is common here also, right? So if you take outside, then here you get this is G1 bar, G0 bar, and here it is G1, G0. So what it is? It is nothing but exclusive NOT function, isn't it? So that is written here, you see. This G3 bar, G2, and here it is XNOR function. So G1 XNOR with G0. So this is taken, this is also taken. Okay, fine. Then you consider these two terms, isn't it? In this G3, G2 is common, so you take it outside. Inside you have G1 bar G0. Here also you have G1 G0 bar. Okay, so it is a XOR function. So it is written here, you see, G3, G2. Then this G1 bar G0 plus G1 G0 bar is written as exclusive. So G1 exclusive OR with G0. So this term is also over. Then the last, so these two, if you refer, G3, G2 bar is common, right? So this G3, G2 bar is taken outside. Within bracket, you get G1 bar, G0 bar. Here we have this G1, G0. So that is written here, plus with the sign plus. So for this case, what it is again? It is XNOR. So we have written this here. G3, this G2 bar. Then this one is G1 XNOR with G0. Okay. So the fourth term is also written. Then if you compare this here, this first and the second term, G1 exclusive OR with G0. Here also you have G1 exclusive OR with G0. This is common. So we have taken it outside. G1 exclusive OR with G0. So within bracket you get this G3 bar G2 bar plus this G3 G2, isn't it? That is our. Then you can combine these two, in which this G1 exclusive NOT with G0 is common in these two terms, right? So it is taken outside. G1 exclusive NOT with G0. So within bracket you can write this G3 bar G2 plus this G3 G2 bar. Okay. So this G3 exclusive OR with G0, here what it's available, G3 bar G2 bar plus G3 G2 means it is XOR function with the inversion. That means XNOR. This is nothing but XNOR, isn't it? So I have written this XNOR as XOR the complement. Plus here we have this G1 X NOR with G0, that can be written as G1 exclusive OR with the G0 the complement, isn't it? Because exclusive OR function and exclusive NOR function are complement of each other. So is this exclusive NOR function is replaced by exclusive OR function with the inversion. Here within this we got this as XOR function, so we have written this. Okay, G3 bar G2 plus G3 G2 bar. Okay, so we have written this. Now if you look at this function again, the G1 exclusive OR with G0, then G3 exclusive OR with G2 the whole dash, plus G1 exclusive OR with G0 the dash, here G3 exclusive OR with G2. So it is, if you consider this as A, this is B, AB dash plus A dash B, like that it comes. It means again exclusive OR function. So we have exclusive OR everything. G1 exclusive OR with G0, exclusive OR with G2, exclusive OR with G3. So we got the expression for this B0. So what is the fundamental thing you should know here about this exclusive OR function? A B bar plus A bar B, that can be written as A exclusive OR B. Okay. Similarly, AB plus A bar B bar, that can be written as A exclusive NOT with B. These two things you should know. Similarly, the one more thing, A exclusive OR B, that is equal to A exclusive NOT B the whole dash, because they are complement. So suppose if you have A exclusive NOT B, that can be written as A exclusive OR B, they complement. These fundamental things you should know. Okay, then only we can substitute that things in order to simplify. Okay, right. So we got the expressions now. For B3 it is G3, B2 it is G3 exclusive OR with G2. That means instead of this G3, if you want, you can place this B3. So it is B3 exclusive OR with G2. Then B1 we got it as G3 exclusive OR with G2 exclusive OR with G1. But we know that this G3 and G2 exclusive OR means that is equal to this binary value B2. So B2 exclusive OR with G1. Okay. Then B0 is G3 exclusive OR with G2 exclusive OR with G1 exclusive OR with G0. Okay. In this, these three terms are actually B1. So we can write it as B1 exclusive OR with G0. So what is the final step? It is the implementation or logic diagram. So inputs are G3, G2, G1, G0 or the inputs. We want to get the output B3, B2, B1, B0. Okay. So how do we get this B3 output? It is taken from this G1. Okay, so we draw four input lines which are named as G3, G2, G1 and G0. From the G3 you take the connection which is nothing but your B3. Then you go for this B2. We want to get the output B2. For that it is B3 exclusive OR with G2. Okay, so what is B3? So it is nothing but this G3. So take the connection from here, then connect it, get the connection from G2. These two are exclusive OR, so you get this B2, isn't it? So then for the third, that means B1 output, you can take it from this B2 along with this G1. So for this B1, you can take the connection from this B2 along with this G1 exclusive OR. So G1 is taken from here, that it is given to exclusive OR gate. So you will get B1. Okay. Then B0, for this B0 output, it is B1 exclusive OR with G0. Okay. So B1 exclusive OR with this G0, then you will get this, okay, B0. So this is the logic diagram. Okay, thank you. Hope you have understood.